meters per second squared. So Christina, my little experiment says that G equals 10.7.
Okay, not bad, but I think you only did the experiment once.
Yeah, and what's wrong with that?
I think every time you do it, you're going to get a different result.
Well, you're absolutely right. I've done this with a whole class, and even though they're looking from the same height, even the same parameters, that they get quite a spread of data.
Yeah, well, one way around this is to use this device, which is called a G-ball, and it automatically measures the time taken to drop. So it's got a button here, and when you release it, it starts the timer, and it stops when it hits the floor. So we can use this to measure G by holding it up against a fix like this, which holds in the button, and then it starts the timer when you release it. Okay, 0.56 seconds, which, if my maths is right, gives us a G value of 9.6 meters per second squared.
Okay, so that's quite impressive, but both these devices measure time to the same degree of precision. They're essentially the same stop clock.
That's right, to 100th of a second. But the great thing about this is that we can do it lots of times very quickly, and we can narrow that spread of data.
Okay, and that's what makes this method more precise. So I guess students might suggest that you use this to take a whole bunch of readings from the same height and take an average and use that average to calculate G.
Yes, and they probably would, but it's always much better to take lots of data and then analyse that data, eliminate any anomalies, and then take an average. But in all of this, we're assuming that G is constant, so we've used the Suvat equations, the equations of uniform motion, which means constant acceleration. So to check if that's valid, we should really drop the ball from lots of different heights and then plot a graph to see if G is constant. So if we plot a graph of S against t squared, if G is constant, then we should get a straight line with a gradient of half G.
Okay, why don't we try that? Okay, that's 0.56. And didn't work that time because I didn't turn it on. And 0.55.
1.4.
There it is. Yep, you ready?
Yep, okay.
Okay. It's 0.54. It's 0.55, very consistent.
There we go. Is that straight?
I don't know what I'm talking about. 0.52.
Be a good one for students working in pairs on this, wouldn't it?
0.53 again.
Oh, good.
I've just realised I've done that awful boy thing of being the one who's doing the stuff.
You're absolutely right. Come on.
Sorry. Okay.
Right, you can write them down.
It's 1 metre this time.
Okay.
It's right at the joint.
0.48.
Yeah.
0.48.
Okay, so this one's clearly anomalous.
Okay, should we plot
1.5
meters?
is 0.31.
Yep.
1.4 metres is 0.30.
Okay, so there's quite a spread on there,
Yeah,
but we did it in a great hurry.
Yeah, no, let's... Okay, so that's not the best graph I've seen, and it doesn't look like the straight line we were hoping for, but you can see the spread in the data.
Yes, and actually you could do it lots of times very quickly and get a lot more data.
One of the advantages of this method is you can see the quality of your data, and unfortunately the quality of ours isn't great.
No, but what I love about doing this experiment with my students is that it's really quick and easy to do, and it actually makes an affordable way of doing this as a whole class practical, since all A-level students have to do this practical for themselves now. Not our finest moment.
I've come all the way up to Newcastle to use a legendary piece of apparatus, the data logger. This is a light gate, and when I drop a ball through it, it starts a timer, the other light gate stops it, and I get a recording of the time taken to fall this distance to the nearest 10,000th of a second. And that's a whole significant figure or two more than a standard stop clock. Like the G-ball, it removes the uncertainties that arise from trying to start and stop a timer by hand. This method is recommended by at least one of the exam boards, but I think there are a couple of problems with it. The first is the most obvious. Few schools are likely to have enough sets of this stuff to allow students to do it as a whole class practical. I think the second problem is more serious. In this arrangement, the ball is already falling by the time it gets through the first light gate. That means our starting velocity is not zero. So in order to plot a straight line graph, we need to do a different rearrangement of our equation, s equals ut plus a half at squared. we end up having to plot 2s over t against t to give us a graph which has a y-intercept of 2u and a gradient of g. Now, this sort of equation wrangling and data processing is absolutely something that A-level students ought to be able to do. But I think introducing it with this practical early on in the course is an unnecessary distraction from the things we really want them to be thinking about. I think you can do this as a demonstration after students have done the practical using another method, and I've got one more to show you. Hi Ronan. I've just been using the data loggers, and you know, as a physics teacher it's always good to have a reason to dust off kit that might otherwise not be used. But I have to say I really don't like the complications it introduces for the data analysis for this practical, and you've got quite a nice way around that.
Sure. I'm going to be using this millisecond timer to time the fall of this steel ball from an electromagnet here down to a switch at the base. The switch at the base is going to stop the clock. Let's take you through it. First of all, open the switch at the base.
Yep.
And then if you press the green button, that will switch on the electromagnet, hold that,
Okay.
and that will then hold the ball up. And if you just tap the red button, that will release the ball and start the timer.
Okay.
Okay. Great. So 0.333 of a second. So if my calculations are right, that should give me G equals 9.72.
That's very impressive, and I really love that this gives us a higher degree of precision than the G-ball and eliminates the problem of the non-zero starting velocity. But if I'm not mistaken, you can buy a kit like this commercially.
Yeah, this is the standard equipment that you can see in many physics textbooks, standard circuit diagrams. And I've tried various of the commercially available kits, and apart from the fact that they're pretty expensive, all the ones I've tried have got problems with releasing the ball cleanly.
And you've managed to overcome that.
So with the kit I've designed, the ball is only held up with a minimum force, so as soon as you stop the electromagnet, it begins to fall straight away.
Yeah, and I've done this as a demonstration using a C.
Sure, yeah, we've all done this in our teaching, that we can put a bit of kit and have a scalar timer with a C-core. It's pretty fiddly to set up, and I don't know about you, but I have found it hasn't given terribly reliable results. So this equipment has been designed so that not only can the students see the circuit very straightforwardly, but it's very easy to set up, releases the ball reliably, and the students are able to get data from it independently. So you could have a whole class set of this equipment, and that would then allow you to do the core practical.
Whatever approach you use with your students, they'll be able to compare their value with a known value for G. And that's not a luxury scientists and engineers usually have. Sure, in this practical, we know the answer we're supposed to get, but that doesn't mean it can't be interesting or useful for students. Scientists and engineers are constantly pushing their techniques and their instruments to the limit to extract reliable data. And those who manage to do that can publish original work. And those scientists who publish unreliable data will be proved wrong by other scientists. That's how science works, and that's what this practical is really about.